The transition from abstract theory to a living simulation is captured through two distinct perspectives. The state diagram, which outlines the logical stages of the system's life cycle, and the sequence diagram, which details the step-by-step interactions required to produce the final output. Both diagrams find their origin in the derivation sheet, which provides the foundational rules governing how an object moves through space over time. The state diagram. A life cycle of motion. The state diagram describes a structured journey that begins with a shared foundation. This engine acts as the brain of the operation, taking the core principles from the derivation sheet, such as how far an object sits from the center and how fast it climbs, to determine every coordinate the object will visit. From this foundation, the process branches into two distinct phases. The static phase. Here, the focus is entirely on the spatial path. The system renders the entire spiral at once, like a map, highlighting where the journey starts and ends. By projecting this path onto a flat surface, it confirms that while the object climbs, its footprint remains a perfect circle. The dynamic phase. This is where time is introduced as a moving variable. The narrative shifts from a completed map to a real-time journey. A blue line begins to trace the path, and a red that appears to represent the object's current location. To make the experience more immersive, the camera itself begins to move, rotating the perspective to showcase the three-dimensional nature of the spiral. The sequence diagram. An operational workflow. While the state diagram shows what the system is, the sequence diagram shows how it acts. It reveals a precise handshake between the mathematical engine and the visual tools. Preparation. The process begins by calculating the constant speed and the total distance traveled. This aligns with the derivation sheet's proof that the object speed never changes, even as it twists upwards. Reporting and drafting. Before any movement occurs, the system prints these physical constants to the user and draws a faint, dotted blueprint of the full trajectory. The animation loop. The script then enters a repetitive cycle. For every frame of the animation, it updates the position of the object and shifts the camera's view. To ensure the simulation runs smoothly without stuttering, the system performs a clever trick. It uses a high level of detail for its internal calculations but a slightly lower number of frames for the actual playback. Synthesis of theory and visualization. Ultimately, these diagrams bridge the gap between the pencil and paper logic of the derivation sheet and the interactive simulation. The derivations prove that the motion is a perfect blend of a steady vertical climb and uniform circular rotation. The diagrams then ensure this superposition is rendered accurately, resulting in a visualization that emphasizes a constant radius and a steady, predictable spiral.